we will discuss the inverse function theorem, but before we do, I'd like to discuss some terminology and notation for functions. Okay. Let A be an interval and f of x a function with domain A. Now, this could be, A could be the function's natural domain, or it could be some restricted domain for the problem you're working on. And then we let capital B be the image of capital A under F. This is also called the range. If you take A to be domain, what this is B consists of all y values f of x such that x is in this interval A. And then some notation we may write F A and then this arrow B. Now I will say, I'm just stating this in terms of a way we can use it for the inverse function theorem. This is a very more general way to write a function. A doesn't have to be an interval, and if you write this, B doesn't necessarily need to be the image of A. B could be larger than the image of A, sometimes called codomain, but for the purposes of our discussion today, we will have this set up. Now, let's look at some examples. And I'm going to start with, well, 3 graphs, so we can think about these concepts graphically. The first one, I'm not going to necessarily give a name to. Let's see, I'll just graph. My function will be in, how about blue? So if I put this here and here, and then 2 is maybe here, okay. So here's a function. What do we see here? The domain, at least what I've tried to graph, is the interval 2 to 5, closed, and this maps to the closed interval 1 to 2. And in fact, as I was saying above, 1 to 2 is the image, You see 1 to 2 is the image because, well, this is where the y values land. Now, let's look, the next 2 are going to be named functions that we have a name for. So here, let's look at f of x equals the sine of x. But I'm not going to graph it on the whole real line. Of course, the natural domain of the sine function is minus infinity to infinity. But I'm going to graph from minus pi over 2 to pi over 2. Sine goes through 0, 0. Sine of pi over 2 is 1. Sine of minus pi over 2 is minus 1. And if I also graph this in blue, it looks approximately like, this. We see here, well, you use this notation that f maps minus pi over 2 onto minus 1 to 1. Now, this part, I could change this minus pi over 2 to 2, this closed interval, to be the whole real line. As I was mentioning, I could write it that way. F goes from minus infinity to infinity onto minus 1 to 1 is also a true statement. Now one more I will graph. This will be e to the x. And this I will just sketch as I am the other ones. This is f of x is e to the x. And this goes to the point 0, 1, and it is exponential growth. Something like this. And f maps, oh, pardon me, open. Minus infinity to infinity onto 0 to infinity. The image of e to the x is just positive real numbers. And I think we used that a few videos ago. Okay, so here are 3 examples, 3 functions where I sort of wrote down some intervals on the left-hand side and images on the right-hand side. For the inverse function theorem, we are interested in a very specific type of function. So we are interested in functions, I'll say f from a to b with b the image and f passes the horizontal line test. Now, you might ask, what is the horizontal line test? Well, you might remember, in order for a function, in order for a graph to be a function, it must pass a vertical line test, which says every vertical line hits the function in no more than one place. So for instance, just to remind you, the vertical line test, and of course this one is different, but the vertical line test allows you to say that something like this is not a function, because here a vertical line hits the graph in more than one spot. But now I'm starting with a function. Okay, so I know it already passes the vertical line test. I know the domain is A. I know the image of A under F is B. This is the range. And then I want it to pass a horizontal line test. So this one's okay. This one's okay, but not this one. In the horizontal line test, it just says that no horizontal line can pass through the graph more than one time. So here, if you do this, it passes here and here. This one, is not one that we would consider in the moment, not for inverse function theorem. Well, okay. This part, passing the horizontal line test, has an adjective. It's called 1 to 1, and the fact that B is the image of A under F has an adjective. It's called onto. If you are interested in further studying those concepts for a function, I would say go take math reasoning. It's a beautiful course taught at this university. Well, and I have videos for that course, but in any case, we don't need that technical terminology so much as the understanding. So this function we can't say much about, does not pass the horizontal line test, but this one does, and this one does, okay? So when you have a function like this, what is nice is when you have both of these, which I mentioned was called 1 to 1, and onto, we have an inverse function. So for this type of function f, we have an inverse function It's denoted like this, and this maps from B to A. So B is the domain of F inverse, and A is the range of F inverse, or the image of B under F inverse. Now, this function, I'll say satisfying. Here is what is wonderful about the inverse function. F inverse of y is x if and only if f of x equals y. And this is the fundamental relationship that you have between a function and its inverse. Now, I'm going to keep this graph, so I'm going to erase this part, and I will say a little bit more about a function and its inverse. Well, two important things that come from this, which I will underline in blue, is that if you take f of f inverse of y, we get y. And this is the function composition, okay? Just like we were just discussing in the chain rule. In fact, I'm going to use the chain rule today, well, when we get there, to see the inverse function theorem. And also f inverse of f of x equals x. And this would be for every y in B and for every x in A, okay? Now, another thing you will see, and this is why I left the graph up of e to the x, is if you stare at what's underlined in blue, what's happening graphically? Well, you see, you interchange x and y. So graphically, f and the inverse function are related by interchanging x and y. Or a way to see that is you flip or reflect across the line y equals x. So let's do that in this picture, and we will see the inverse function for e to the x. You probably know what it is already, but here's the line y equals x, okay? Now what happens when I flip this over this line? Oh, I don't even know what color to use. How about pink? This point, the point 0, 1 goes here, 1, 0, and then this arc goes here, and then this part going towards the x-axis will come down towards the y-axis. This is the graph, so here, this is the natural log. F inverse of x is ln x, okay? And this is a beautiful relationship between a function and its inverse. Interchange x and y, or equivalently, you flip the graph of the function across the line y equals x. And this part, this passing the horizontal line test, when you flip across the line y equals x, you're guaranteeing that this new thing, which I have in pink for this example, passes the vertical line test, meaning it's a function, okay? Now for the calculus. The first however many minutes of today's video felt a little bit like math reasoning, but now comes the calculus, which is why I was talking about all that stuff. And this is the inverse function theorem. So suppose f of x is differentiable on an open interval I, and the derivative is not equal to 0 on this open interval I. Then we let j be the image of f over I. So j is, well, it's the range if you consider the restricted domain being I, okay? Now, the statement is that then the inverse function which goes from j to I is differentiable and we get a formula for the derivative of the inverse function without actually having to calculate the inverse function itself. So the formula is this, that f inverse prime at some value b, it's 1 over f prime of f inverse of b. Now, I have a few things to say about this, and then we're going to do some examples. The first thing that I want to mention is just to talk about some of the hypotheses here. First of all, we need differentiable, we need an open interval I, and we need the derivative is not equal to 0 on I. Maybe I'll put stars here. This part, the derivative not being equal to 0, will guarantee, well, we know the derivative exists because it's differentiable and not equal to 0 on the whole open interval. The derivative will either be positive, function's increasing, passes horizontal line test, or derivative negative on the whole interval, function's decreasing, passes horizontal line test, okay? But moreover, you need the derivative to not be 0 because we're dividing by the derivative evaluated at something. So this is an important hypothesis, that f prime of x is not equal to 0 on I. And it's something that you need to check, okay? So when you're working an inverse function theorem problem, make sure you write down an open interval I. Make sure that you verify f prime is not 0 on I, and then this is the result. Now, the other thing I will say is, how do we get the formula? And this is worth mentioning. We know let's see, I'll do it this way. Compose f inverse of b is, maybe I'll write x because I want a variable, is x, okay? This is definitely true. Well, let's just differentiate both sides, okay? Derivative of x with respect to x is 1. Now, if I differentiate a composition, this is a chain rule. So we would have derivative of the outside evaluated at the inside times derivative, I'm going to move this, of the inside function. And this was equal to 1. Derivative of the outside evaluated at the inside times derivative of the inside function, chain rule. Okay? And then finally, we're trying to solve for the derivative of the inverse function. You see, we get 1 over f prime of f inverse of x. Okay? So this is really where this comes from. Here's our first example. F of x is x cubed plus 1/2 x squared. And then we're told for x bigger than or equal to 0, we want to calculate f of 2 and calculate f inverse prime of 10, and then we will do part C. We'll find the equation of the tangent line to the inverse function at x equals 10. Okay. Well, parts A and B came off an old final exam, and part C I'm adding so that we can look at a graph. Very nice. Part A, find f of 2. Well, this is quite straightforward. We just evaluate the function at 2. We get 10. Part B, calculate f inverse prime evaluated at 10. This is when we are supposed to use the inverse function theorem. Now, we don't want to actually find the inverse function, okay? So, what do we know? Let's move back here. This means that f inverse of 10 is 2. This is this relationship, okay? Now, let's find the derivative, and here's where I'm going to have an open interval I, make sure that the derivative is not equal to 0 on I. All of that we need in the inverse function theorem. The derivative is 3x squared plus x. Well, we're given here greater than or equal to 0. I will use the open interval like this. And now the derivative is positive on I. Okay? So we have an open interval. The function's differentiable on the open interval. The derivative is not equal to 0 on the open interval, so we may use the inverse function theorem. Okay, so we get f inverse prime of 10. This equals 1 over f prime of f inverse of 10. Now, part A set us up to be ready for f inverse of 10, right? Because f of 2 is 10, f inverse of 10 is 2, and so we need 1 over f prime of 2. Well, that's not too terribly bad. Here's f prime we may evaluate at 2. F prime of 2 is 12 plus 2, 14. And so f inverse prime at 10 is 1 over 14. Okay, this is the end of B. Now, the final thing I have C, it seems I don't have any space. But I have everything. So in fact, I can probably fit C right here. So let's think about C, the equation of the tangent line. This is the graph, y equals f inverse of x. And this right here, it says that the point 10, 2 is a point on the graph of f inverse and on the tangent line, and this is the slope. We would have y minus 2 equals 1 over 14, x minus 10. This would be an equation of the tangent line to the graph of the inverse function at x equals 10. So now here is a graph, and we can see just how I have plotted it. I wrote x is a function of y with the original function, and we know that's plotting the inverse function as a function of x. And we see the tangent line at x equals 10. Here we go. Second example. We have f of x is x squared plus 2 over x for x bigger than or equal to 1. Calculate f of 2. Calculate f inverse prime of 5. It's very similar to the last problem. F of 2, this is just evaluating this function. This is 2 squared plus 1, 5. And this means, from this relationship, between a function and its inverse, that f inverse of 5 equals 2. Okay. Now part B. And again, I start by calculating the derivative because I know I will be using the inverse function theorem. So here, when I differentiate 2 over x, this is really 2x to the minus 1 will be minus 2x to the minus 2, or the derivative is 2x minus 2 over x squared. Now, I will use open interval I to be open 1 to infinity. And now, notice f prime of x, well, at 1, which is not in my open interval, but at 1, the derivative is 0, 2 minus 2. And if you're bigger than 1, if x is bigger than 1, this number will be bigger than 2. And you're subtracting a number that is less than 2, right? So you have a number bigger than 2 subtracting a number less than 2. Without a doubt, this is positive on this open interval, okay? This means we can use the inverse function theorem. So using the inverse function theorem, we get f inverse prime of 5 equals 1 over f prime of f inverse of 5. And through part A, we already know f inverse of 5 is 2. And this is the way I always do the inverse function theorem problems. I always think about this part. I figure out that number first. And then I just have to evaluate the derivative at that number. Well, and take 1 over. Okay. So we have this part. So this is 1 over f prime of 2. And then f prime is here. F prime of 2, maybe I will write this here. This is 4 minus 2 over 4. 4 minus a half is 7 halves. This is 1 over 7 halves. Typically, we don't want to leave a fraction in the denominator, so we invert multiply. This is 2 divided by 7, okay? This will be my last example. Use the inverse function theorem to find f inverse prime of b. For this function, b is a third, and we're given an open interval I. So we need to check that f is in fact differentiable on I, that the derivative is not 0 on I, and then we can use the inverse function theorem. But if the first question, see, we don't have the A and the B that we had in the last two. So we need an A with f of A equals 1/3. So let's just look at this. What x value satisfies f of x is 1/3? Well, you can see it pretty quickly. X equals 0, right? F of 0 is 1/3. And then this will tell us f inverse of 1/3 is 0. Okay? Now let's take the derivative. Well, you see we have a few choices here. We can quotient rule, numerator, denominator. We can chain rule, because really we have all of this to the -1. Maybe I'll do a chain rule. For the chain rule, my original function is x squared plus x plus 3 to the -1. Now you see the inside and outside function. So then f prime of x, it's minus 1, well, big parentheses, to the minus 2. Inside the parentheses, we put the entire inside function, and then we multiply by the derivative of the inside function, 2x plus 1. And now we get negative 2x minus 1. I'm just distributing this negative 1 across here. Then I move this into the denominator. So x squared plus x plus 3 squared. I would have arrived at the exact same thing using the quotient rule. Okay, well, where's the derivative? 0. Where's the derivative? Undefined. We need to make sure this function is differentiable on all of I. So this is a very good thing to think about. The derivative does not exist when the denominator is 0. This would be negative b plus or minus square root b squared minus 4ac all over 2a. But you see here we're going to have a negative square root. So that does not happen. This is a irreducible quadratic. Let me erase this part and I'll just say f prime of x exists on minus infinity to infinity. Okay. F prime of x equals 0 when minus 2x minus 1 is 0 or x is negative 1/2. But this is not in my interval. And so here we get the derivative is not equal to 0 on I. Okay? So the function is differentiable on I, the derivative is not equal to 0 on I. We may use the inverse function theorem. Okay. So I will do that over here. Now let's compute f inverse prime at 1/3 equals 1 over f prime of f inverse of 1/3, which is f inverse of 1/3, we see it's 0. So this is 1 over f prime of 0. And now we have the derivative here. We just need to evaluate this as 0. So maybe I'll do that underneath. F prime of 0 equals what's negative 1 over 9. Okay, and this gives f inverse prime of 1/3. It's 1 over this, which is negative 9. Okay, so this is the inverse function theorem in action for this problem.